The P.O.W.E.R.G.R.I.P.S system is a technology developed to allow amputees who communicate through sign language to have the ability to sign again. Today, sign language is recognized as a fundamental language in our society. People who sign are a wide-ranging group, including those with hearing loss and their loved ones, and several are amputees or disabled in a way that doesn't give them the dexterity to form hand signs. There are already significant efforts to develop bionic prosthetics that have the required dexterity, and these research efforts have already been ongoing for years. There aren't, however, ways to communicate with these bionic limbs. With the P.O.W.E.R.G.R.I.P.S system, the user still has functional use of the controlling arm. The wearable gauntlet design can read the 18 degrees of freedom of the able arm, while not impacting the actual operation and range of motion. For a proof of concept, the design sets out to produce a wearable technology able to be fabricated within budget and on time. The physical prototype is 3D printed, and all the electrical components can be purchased by the public. This information can then be sent into 2 separate software programs, one for displaying a one-to-one representation of the movement. It also stands in as the final implementation given a working bionic. The other program is the learning algorithm that is trained for recognizing gestures from the patterns within the data. This software needs to be implemented for the nuance and complexity in the sign language library to be coded. To develop the P.O.W.E.R.G.R.I.P solution, the task was divided into 3 main categories based on the engineering disciplines required: biomedical, electrical, and software. Within the biomedical realm, some of the most important considerations for building the gauntlet are the clearances of the assemblies and preserving the dexterity within the hand. The design begins with measuring the parameters of the user's hand. These determine the overall dimensions of everything in the prototype and acts as the foundation. There are several limiting factors, for example, the development of the rail system for pivoting the knuckle joints. This assembly mechanism needed to fit in between the fingers without forcing them to be splayed. The pivots of each joint needs to be co-located with the physical bone inside the hand. Some bones, especially in the thumb and wrist, involve multiple degrees of freedom around the same point. For the design, each of these connections needed to be analyzed. They were all isolated and paired within a specific potentiometer for measurement. Each finger assembly shares the same basic design, but needs to be adapted and scaled for each one. The prototype was printed in PLA plastic filament due to the rapid iteration and strength. With the full prototype designed and assembled, the movement dexterity is tested and ironed out, then sent into the stage of fitting the electronic components. For the electrical engineering side of the design, potentiometers were selected due to their range of resistance, travel length, and overall size. An Arduino Uno microcontroller is used for commanding the potentiometer readouts. There is a challenge with the Uno being limited in its channels. The 18 degrees of freedom require the same number of analog channels for the signal and several more digital channels for power. For this reason, a multiplexer was used to turn 1 of the 6 analog and 4 of the 12 digital channels on the microcontroller into the equivalent of 16 analog channels. Within the code itself, these are switched from one to the other and referenced all quick enough that it's imperceptible. All 18 values of the potentiometers are continuously written locally into a file, several times in a second. With all the potentiometers wired through the breadboard for troubleshooting, powered through the multiplexer, and controlled through the Arduino, they are all tested and then physically attached to the prototype. After troubleshooting all the connections, the system is tested to show that the readings from the potentiometer are written to the file correctly. Finally, the software side of the system can read this file and interpret the information. The data on the file is constantly being updated. For a visual display of the hand movement, the Unity game engine is used. The game engine is a stand-in for the application on a bionic limb. With the entire system active, the display clearly shows the dynamic movement of the physical prototype being translated into motion on a digital hand. The other aspect of the software development is the machine learning algorithms for recognizing the gestures input into the gauntlet. There are two classifiers used, one to recognize the specific positioning of the hand and the other for the sequence of motion. These two algorithms work together to identify the gesture. For example, specific to sign language, the sign for the letter T and the word bathroom are the same hand sign, but bathroom also includes wrist movement. To accomplish this, a scikit-learn's k-nearest neighbors algorithm is used for both classifiers. A graphics user interface, or GUI, is developed that lets the user train the identifier by positioning the gauntlet and recording this position into a drop-down menu. As more and more identifiers are logged, the system accurately increases and flags specific gestures when they are matched. This interface is crucial for the long-term effectiveness of the system, allowing it to output these identifiers into the Bionic. The demonstration shows that we were able to successfully implement the biomedical, electrical, and software design to make a working prototype that can take inputs from the gauntlet through potentiometers and output movement from the virtual hand in Unity. We were also able to show that the gauntlet has enough dexterity to make a wide range of signs, as well as pick up a wide range of objects. This information could be identified by the machine learning algorithm to eventually start flagging specific gestures. The gauntlet shows only the 4 fingers for simplicity. With the thumb having multiple degrees of freedom in itself, it was decided that this could be left as a future project. In conclusion, it can be shown that the P.O.W.E.R.G.R.I.P.S design can interpret a wide range of hand movements and identify basic movements through machine learning. However, the design does not end here. By implementing the design and reading the 18 degrees of freedom in the able arm, while not impacting the actual operation and range of motion, the prosthetic arm could either follow these movements or do the reciprocal movements that go with that sign. This design could be used for more than just sign language. It could also be a way for amputees to regain some of their lost movement.